All right, hello everyone. My name is Jakab, and I'll be talking about the spectral sparsification of hypergraphs. This is joint work with Michael Kapralov, Robert Krauthgamer, and Yuichi Yoshida. So first of all, what is graph sparsification? Graph sparsification is simply the process of compressing a potentially dense input graph into a reweighted subgraph of itself in such a way that some crucial property of the original graph is preserved. So in the case of cut sparsification, for example, which was introduced by Carter in '94, we want to preserve the sizes of all cuts simultaneously. So for this, obviously, the subgraph will have to be upweighted. And in the more powerful notion of spectral sparsification, which was introduced by Spillman and Tang, we want to preserve the quadratic form of the Laplacian of the original graph on all inputs. So this is more powerful because you can plug the indicator vector of a cut into the Laplacian and onto the quadratic form of the Laplacian, and you can recover the size of the cut, but you can also do many other interesting things with the Laplacian. So both of these concepts have been generalized to hypergraphs in recent years. The generalization of cut sparsification is fairly straightforward because the size of a cut is still well defined in a hypergraph. Now, in order to generalize spectral sparsification hypergraphs, we need to define an analogous notion to the quadratic form of a graph. And so this is how it's done. The quadratic form of an ordinary graph is simply the squared stretch summed up over all of the edges. And this is still the case for hypergraphs, except that the stretch is defined as the maximum distance between any pair of vertices in an edge, as opposed to the distance between the only two vertices in the edge. And so this nicely generalizes the same concept for ordinary graphs. It also has the analogous property that if you plug in the indicator vector of a cut, you'll return the size of the cut in the hypergraph. And it has lots of other nice properties and applications in various fields. And so we can define spectral sparsification as reducing a potentially dense input hypergraph to a reweighted subgraph in such a way that this Q function is approximately preserved on all inputs. And now both of these concepts have been studied in recent years, both cut and spectral sparsification in hypergraphs. In their recent work, Chen, Kana, and Nagda showed that nearly linear sized cut sparsifiers exist for arbitrary hypergraphs. And we show the same result for spectral sparsification in our paper. So for the rest of the talk, I'll try to give you some idea on how this is done. So in general, what does one do if one wants to construct spectral sparsifiers? One of the main techniques for doing this is importance sampling. So this is a very simple technique. You just assign importances to each edge based somehow on the global structure of the graph. And then you sample each edge independently with probability proportional to its importance. If you don't sample an edge, you discard it. And if you do sample an edge, you upweight it with 1 over its probability. So in this way, in some sense, the subsampled graph becomes an unbiased estimator of the original graph. And more formally, if we are interested in particular in the quadratic form of the Laplacian, we can say that for any input vector, the quadratic form of the subsampled graph is an unbiased estimator for the quadratic form of the original graph. And Spillman and Srivastava shows that you can get nearly linear sized spectral sparsifiers for ordinary graphs if you select the importance to be proportional to effective resistance. And this is essentially the same thing that we'll be doing. So we'll also set importance to be proportional to effective resistance. And we just want to generalize this technique to hypergraphs. Now, the main difficulty in doing this is that essentially what one needs to prove here to show correctness of this technique is a matrix concentration, the concentration of a random matrix around its expectation. So typically tools like matrix Bernstein are used or similar tools to that. And these translate really poorly to the realm of hypergraphs for the simple reason that the so-called quadratic form of the hypergraph is not really a quadratic form. It's not really a linear function. Because we're taking the maximum over vertices in the edge. And so such techniques simply don't translate. And in order to have a chance at doing this same thing, for hypergraphs, we need to have an alternate proof for ordinary graphs that doesn't use tools like matrix Bernstein and proceeds more directly through a counting argument. So this is exactly what I'm going to do in this talk. So I'll be talking mostly about ordinary graphs. And what we want to prove is that if we sample with probabilities proportional to effective resistance, then we have this concentration around the expectation simultaneously for all vectors x. Now, of course, for a single specific vector x, we could easily prove this using Chernow bounds. But the problem is exactly that we need to prove this simultaneously, right? Especially because there are infinitely many possible values of x. This is a continuous variable, but we're not going to be deterred by this. What we're going to do is propose an epsilon net to discretize the space of all possible x's. So we can round x to some x tilde, such that x tilde takes only a finite number of possible values. And then we can proceed by by proving concentration using Chernow bound for each specific x tilde, and then combining it for all x tilde using unit bounds. So this is the plan. So let's take a closer look at that Chernow bound. Indeed, what we are looking at is the concentration of a sum of random independent variables around its expectation. So Chernow bound works perfectly. And as it happens in Chernow bounds, the power of the bound is dependent on the maximum possible size of any individual term in the sum, right? So if all the terms in the sum are individually very small compared to the expectation of the sum, then we get a very powerful concentration result. But conversely, if even one term can take on high values, then the concentration inequality is much weaker. So the failure probability of the Chernow bound is much higher. And in our specific case, each random variable corresponds to an edge in our graph. And the maximum possible value that such a random variable can take is simply equal to the squared stretch of the edge divided by its resistance. And so we call this the power of the edge. And if you take a close look at the exponent in this Chernow bound here, you can figure out that in the worst case, this can be as low as a constant, which is really bad. There's really no hope of producing a discretization scheme that is coarse enough that we can still apply union bound over it. So we need to do something more clever. And the more clever thing that we're going to do is we're going to categorize edges based on their power. So now we can write up these Chernow bounds independently for each category of edge. So if we restrict our view to just the category EI, then we get the same concentration inequality, except that because we have some idea about the power of the edges that are in the sum, we have a much more refined upper bound on the failure probability here. And this scales exponentially in the power of the edges present. So I can say that this is a stronger Chernow bound because in the cases of the most powerful categories, this is just as bad as the original, but it's at least more refined. And so we can do something here, which is that we can, instead of defining an epsilon net that is universally good, we define epsilon nets specialized to each category and each power level. So for some category EI, we're going to define a mapping x to x tilde of I. That's going to be our discretization for that level. And there's a trade-off here that is dependent on I. So if you look at a high power category, then of course our Chernow bound will be as bad as the original. And so we can't really afford to take a union bound over a very fine discretization. So we'll need a very coarse discretization. But the good thing is that because we're only looking at high power edges, the requirements for the approximation properties of this discretization are much weaker. They're much relaxed. And this is because most edges are low power. So there's only a very few number of high power edges, and they're also distributed very predictably across the graph. So we can actually get away with discretization to fewer vectors x tilde. Conversely, if we look at a low power category of VI, then of course the channel bound is much more powerful. We can afford to take the union bound over a much larger epsilon net, and so we can afford to have a finer epsilon net, the better approximation. So this is the intuition behind why it works. Now, I'm not going to go into detail on how we actually construct this rounding, but I'll just point out the main tool which we use, which is something called the resistive embedding. So the resistive embedding is basically a technique for mapping vertices, or in this case, edges of the graph, into Euclidean space in such a way that effective resistances show up as the L2 squared norms of vectors. And in fact, we also embed our vector x into this space. And this results in all kinds of interesting quantities showing up as L2 squared norms or as scalar products. In particular, the total energy of the vector x, the effective resistance of each edge, and also the square stretch of each edge. So this is every quantity that characterizes our rounding problem. And so we can reformulate our rounding problem entirely in terms of these vectors. And you can see here that actually the lengths of the vectors completely cancel out. And what we're left with is only the angles of the vector that matter. So if the vector corresponding to an edge is more or less parallel to the vector corresponding to x, then that edge is a high power edge. And if a vector like E2 in the picture is more distant from being parallel, then that's a lower power edge. And in any case, if you reformulate the rounding problem entirely in terms of these vectors, then you get a much cleaner problem. And this has actually been studied before. So what you get is the compression of approximate scalar products up to an additive error, which has been studied by Allen and Krauthgamer in 2017. And their result gives us exactly the rounding scheme that we're looking for. So this is great. This essentially concludes the proof, but just to have another summary, what we're doing is we want to prove concentration of this quantity x transpose L tilde of x around this expectation. This is a sum, so we break it up into we break up the terms of the sum into categories, and we take the subsums over each category. We prove concentration for each category individually. And the way we do that is we propose a specialized rounding scheme, which was defined specifically for that category. And we show that we can replace x with x tilde in this inequality. And to prove the inequality for x tilde, we can simply use a combination of union and Chernow bound, because now the number of possible values that x tilde can take is bounded. All right, so far I've only talked about ordinary graphs, so I should talk a little bit about hypergraphs as well. How do we generalize this technique to hypergraphs? So one of the main ways of generalizing algorithms from ordinary graphs to hypergraphs is something called a Clique expansion. If you have a hypergraph, you can replace each hyperedge simply with an ordinary clique. So this will result in an ordinary graph with a huge number of parallel edges, but in any case, an ordinary graph. And you can run whatever algorithm or optimization you want on the ordinary graph and interpret the results in the hypergraph. So this works in a lot of settings. And in fact, it also works in our setting. In the case of constructing spectral sparsifiers, the problem is that such a naive Clique expansion doesn't really capture the spectral properties of the original hypergraph. And so if you really want to construct a spectral sparsifier using this technique, you're going to start losing factors of R in the size of the hypergraph. So you need to do something a little bit more clever. And the little bit more clever thing that you can do is to use something called the balanced weight assignment, which is introduced by Chenkana and Nagda in their paper where they achieve the nearly optimal cut sparsification for hypergraphs. And the idea is simply this. Instead of producing uniformly weighted cliques from each hyperedge, we can produce arbitrarily weighted cliques from each hyperedge. We can shift around the weights among the edges of the clique as desired to achieve some property that will be useful for our specific optimization problem. And in the case of sparsification, what this is that if we're doing importance sampling, we really want all the importances of all the edges in the same clique to be more or less the same. We can't have them be exactly the same, but we can require them to be more or less the same. So the crucial property is this, that for any pair of edges fg that reside in the same clique of the clique expansion, we want their resistances to be approximately the same, unless the weight of one of them is 0. And we'll see in a second why this second clause is important. So why would we expect such a weighting to even exist? This seems like a very specific requirement to have. Why can we expect that such a graph will even exist? Well, what gives us hope is that you can always at least locally fix violations of this rule. So suppose this rule is not respected by a pair of edges f and g. So that would mean that the resistance of f is much higher than the resistance of g. In this case, we can simply shift weight from g to f. Right? We can do this because they reside in the same clique. And this will actually solve our problem, because if you shift weight away from g, then its resistance increases. If you shift weight onto f, its resistance decreases. So these resistances will tend towards each other, and we can keep shifting weight until one of two things happen. Either the resistances become equal, and then the violation is no longer there, or simply g runs out of weight, in which case the second clause of this rule is satisfied, and again, the violation is gone. So that's nice. We can go around the graph looking for violations of this rule 3 and fixing them locally. And this is indeed more or less what we do in our algorithm. But it's very far from obvious that this will actually terminate. Like, one could conceivably get into loops of fixing the same violations again and again. Because doing such a weight shift can have very unpredictable and very widespread implications on the rest of the graph. It changes effective resistances throughout the graph in ways that are very difficult to categorize. But luckily, there's a very simple idea that can help us prove that this process actually terminates. And we do this through the use of a potential function. And actually, somewhat surprisingly, our potential function is just the total weight of all spanning trees on the graph. So we sum over all possible spanning trees, and we take the product of the weights of the edges of the spanning tree. And this will actually give us a potential function that is useful in analyzing this process. And the reason for that is mostly due to this very surprising and famous relationship between resistances and spanning trees, which is that the resistance of an edge is simply the probability that that edge participates in a uniformly random spanning tree of the graph. So if you know this property, you can fairly simply derive an update formula for this potential function based on which is going to relate to effective resistances. So if you increase the weight of some edge, then the potential function also increases, and it increases proportionally to the effective resistance of that edge. And similarly, if you reduce the weight of some edge, then the potential function decreases, and it again decreases proportionally to the resistance of that edge. And this is exactly what we want, right? Because we're always shifting weight from low resistance edges to high resistance edges. This means that our potential function will always increase throughout this process, and this precludes the possibility of getting into these cycles. And of course, naively, this will still be an exponential runtime algorithm, but there are various tricks that one can apply to fix that. And so just to have an overview, our full algorithm is the following. We construct this balanced weight assignment of H, the input hypergraph. We compute the resistances of each edge in the weight assignment G, and then we assign importance to each hyperedge that is equal to the maximum resistance among edges in its clique. But remember that most edges have the same resistance, more or less, in the clique. So this is basically just the consensus resistance in the clique of the hyperedge. And finally, we just use importance sampling on the hypergraph, and this will give us a nearly linear sized spectral hypergraph sparsifier. And there are also various speedups that we can apply, because the naive implementation, as I said, is quite slow. But these are just small tricks. And I guess I'm out of time. So thank you for your attention.